guys, so let's review conservation of momentum. So far we've seen a quantity called impulse, which is represented by the letter J, and that is calculated by the applied force times the change in time, and the units for impulse are Newton seconds. We've also seen a quantity called momentum, represented by the letter P, calculated by mass times velocity, and having the units of a kilogram meter per second. We also saw impulse momentum theorem, which equates the impulse to the change in momentum. Again, this is not impulse equals momentum. This is impulse equals a change in momentum. So J equals delta P, or F delta T equals M delta V, where M delta V equals MVF minus MVI. But what about a system of two or more objects? We've been looking at one-dimensional momentum, and we even saw two-dimensional momentum in our hockey puck problem. So now let's consider a system that's composed of more than one object. We can consider the simple system of billiards with two balls, ball A and ball B. So here we have ball A, which starts with some initial velocity, VAI, and ball B with mass B that has an initial velocity of 0. We can consider the two balls colliding, which is what you see here in the center. And then finally, ball A is brought to rest by the collision, or by the impulse of the collision, and ball B now gains a final velocity of VBF. So if we were to calculate this problem with numbers, with real measured numbers, we would find out that the initial momentum was exactly equal to the final momentum. That also means in this case, the change in momentum for ball A is equal and opposite to the change in momentum of ball B. So the momentum that is lost by ball A is gained by ball B. Looking here at our equation, if we add the delta PB to both sides, we get the change in momentum of ball A plus the change in momentum of ball B equals 0. So our conclusion is that in the absence of external forces, meaning there's no friction, there's no air resistance, the total momentum of the two objects remains unchanged before and after the collision. Or, said more simply, the total momentum of the system is conserved. Now this is going to hold true from this moment on through the rest of the chapter. So even when we start to incorporate ideas such as energy and whether or not energy is conserved, you will know that momentum is always conserved for our purposes. This is even true when you take a jump. So when you impart an impulse upon the earth to change your momentum and jump, the earth experiences a change in momentum that is equal and opposite to the momentum change that you experienced. Now the reason that we can't really observe this change in momentum in the earth is because the mass of the earth is so large that the change in velocity is so small. It's not even observable. But it does happen. So mathematically, there is a change in the earth's velocity when you jump. Now, my favorite part, and everyone's least favorite part of our discussion is, well, where did this equation come from? Remember, we don't just make up these equations out of thin air. They're always built upon some previous idea and then derived in our class algebraically, in some classes through calculus, but derived from other equations. So they don't just pop out of thin air. So for conservation of momentum, let's take a look at Newton's third law. Remember that Newton's third law said that the forces occur in pairs and that these forces are equal and opposite in magnitude. So let's consider the simple case of a large truck M1 colliding with a very small truck of mass M2. So here they are colliding. And let's state everything that we know about the force of M1 on M2 and the force of M2 on M1. Well, the force of m1 on m2 and the force of m2 on m1 are Newton's third law pairs. They are equal in magnitude and opposite in direction. And logically, we can reason that they act on each other for the same amount of time, delta t, meaning the big truck cannot push on the small truck for a different amount of time that the small truck pushes on the big truck. Then if that is indeed true, if F is equal and opposite for each object and delta t is the same, then that means their impulses are equal and opposite. Or F1, meaning the force on mass 1 by mass 2 times delta t, is equal to the opposite of the force on mass 2 by m1 times delta t. If F delta t is equal and opposite for each of these objects, then the impulse is equal and opposite for each of these objects. If the impulse is equal and opposite for the truck and the car, then the change in momentum is equal and opposite for the truck and the car. And that comes from, again, impulse momentum theorem, where impulse is equal to the change in momentum. So if impulse is equal and opposite, then the change in momentum is equal and opposite. Again, I would never have you doing something so algebraically complex on the test, but I do want you to know where these equations come from. Now, what you see here in the pink and the blue, right here at the bottom of the screen, is that exact statement that the impulse is equal and opposite, and therefore the m delta v is equal and opposite. And this entire thing simplifies to initial momentum equals final momentum, or that momentum is conserved. Yay!